Subir, you're mute.
Oh, sorry. How you? It seems like you're the host. Can you make me the host? How you? Ah, okay, there. I'm host. Thank you. Sorry about that. I just, I think I know what I did wrong. Oh, that's not work. Okay, well, forget that. All right, well, we'll just go with the Zoom recording then. So you can all hear me? Everything's good? Okay.
Yes.
And let's see if I can share my screen. All right, so I presume you can all see the phase diagram here of the Bose-Hubbard model that we've been discussing. Okay. All right. So far we've talked about a variety of phases of matter. Starting with the most familiar and common ones: the Fermi liquids, superfluids, superconductors, and then we also talked about with strong interactions, bosons can form insulators. But the type of insulators we met so far are fairly trivial. They just have integer filling, like in this n=1 mod insulator of bosons. All right. So today we want to really introduce a whole new concept. And the way I'm going to do it is initially by just presenting the basic idea through a lot of hand waving, just some trial wave functions that people have thought of over the ages. And this concept is one of fractionalization, that there can be phases of matter in which the underlying particles that you start with on the lattice don't end up to be the particles that finally appear at low energies in the theory as many body excitations. Now, of course, there's a simple way particles need not appear as the lowest energy excitation. They could form bound states of various types. But that's not what I'm talking about. We're not taking particles and making composites of particles. We're taking a particle and somehow it just falls apart. And one of the places where such a remarkable thing is likely to happen is, God, what's going on today? Everything is acting strange. Okay. All right, so that's done. All right. Okay, so I think you can see my screen. All right. Okay. All right. So one of the places that could happen, something remarkable could happen, is right here, and that's really the point we're going to focus. Similar thing could happen right over here, and what's special about those points is that there's a huge, in fact, right at that point, there's a macroscopic degeneracy of the ground state. There's many states, in fact, an exponentially large number of states that have the same energy. So at this point, for example, the energy of the state with 0 particles per site is the same as the energy of state with 1 particle per site. Here, E of n is minus mu n plus u over 2 n times n minus 1. And similarly over here, then E of 1 is the same as E of 2. And so basically, you can then say if you're going to focus on this region, we're just going to look at states with 0 and 1 particles on that site and ignore everything else. And then because there's a huge macroscopic degeneracy, you expect that any small perturbation that you might add is going to lift that degeneracy in that degenerate subspace. And the question we want to ask is what are the possibilities of things that can happen? So we'll just focus on this case here, whether these either empty or 1 boson per site. So effectively, that means that the bosons are hardcore because you can never put, they have infinite repulsion between them. You can never put 2 of them on a site. And on each site, effectively, you have a qubit. You have or a spin. It's like you have a spin a half system with either with two states on each side. And we want to now, therefore, so everything we study will also have correspondence in spin models, which is really often the way these things appear in condensed matter physics. But really, in fact, there's a one-to-one mapping between hardcore bosons and in this case, spin a half. So if you have now I call this boson capital B to distinguish from other bosons that will appear later on, where this capital B boson is going to fall apart into half a boson. So we have this constraint that this boson is less than or equal to 1. And so there's two states on each side. I'm dropping the I index now, either the empty state or the state with one boson. And in the spin language, that corresponds to having spin up or spin down. So there's some fictitious spin model where spin up would be spin down. And then you can make a very simple correspondence between the boson addition operator, well, that's just the spin raising operator, the boson annihilation operator, the spin lowering operator, and SZ, well, it's minus a half for the empty side and plus a half for the full side. So that's the operator B dagger B minus a half. So this tells us that if you want to work in states where B dagger B expectation value is 1/2, that's this point right here, that we should work in states that have SZ, average SZ equal to 0. And that'll give us half filling of bosons with very strong on-site repulsion. All right, so now, we can take either language and try to make a guess as to what are the possible states the boson will form when you added some other additional interactions to not just the pure Hubbard model, but maybe you added something else. Oh yeah, so I've already said that. And so as an example, we could consider this particular model. So the bosons can hop between neighboring sites. And then you can put in a repulsion V between nearest neighbor sites. This could be almost on any lattice for now. So there's repulsion between bosons on site I and site J. Now, if you use the operator correspondence I had the previous slide, you would write this as the following spin model. The hopping turns out to correspond to what's called an XX exchange, XX plus YY. And if the hopping has the sign minus W, then this corresponds to a ferromagnetic exchange, meaning the spins X and the spins like to lie in the XY plane and point in the same direction because of this term. And the boson repulsion, well, it gives you, so you just write the Bose operator in terms of the Z operator. Well, there's a +1 that just changes the chemical potential, so we don't worry about that. So this just gives you ZI, ZJ. So this is a term which is a spin exchange interaction in the Z direction. So that's why this type of model would be called an XXZ model, where you've got a X exchange W and a Z exchange V. XXZ meaning the X and Y exchanges are the same. So if somebody says I have an XYZ model, well, then the XX coupling is different from the YY coupling is different from the ZZ coupling. Okay. So we could say, well, what we are interested in are possible phases of the XXZ model on various lattices. Okay. So what are some possible phases? Well, one thing the bosons can do is form this checkerboard, which I've already discussed. So they repel each other. And so now this state is perfectly happy because there's no boson. No boson has any boson on its neighbor site. So the V repulsion doesn't cost any energy. And so this would be the checkerboard state. And this breaks the symmetry. Breaks the symmetry because there's two possible checkerboards where you interchange the empty and the full sites. And so this is still an insulator, but it's got a broken symmetry. And in the new unit cell, if you took some unit cell here, like a diamond like that, if you just translate that diamond through the lattice, you get the full lattice. So it tells you the unit cell has two sites, And so per unit cell in the new ground state, there's an integer number of bosons. All right, and in the spin language, this would be a Z antiferromagnet. Half the spins would be up and half the spins would be down. So the exchange interaction in the Z direction is antiferromagnetic. Okay, what else could happen? Well, it could just turn out to be a superfluid, which is what seems to happen in the Hubbard model when you turn on W a little bit. And so right here, the superfluid is, of course, a condensate of B and B dagger, which is not equal to 0. What does that correspond to in the spin language? Well, if you go back here and look at the operator correspondence, B or B dagger is the same as the operators X or Y. So that corresponds to a ferromagnet, but in, say, in the X direction, but could also point in the Y direction or any angle between them. Okay. All right, so those are phases we already talked about. How about something else? So here's another one, which probably doesn't occur for the XXZ model, but could occur for some other related model. It's called a valence bond solid, at least in the spin language. So in this language, if I take the boson point of view, I have one boson for every 2 sites. So what the boson is doing is just rattling back and forth between these 2 sites. So it's in this coherent superposition. There's one boson. It's either on site 1 or on site 2. And this is rattling back and forth. And in the spin language, when the boson's on site 1, the spin on site 1 is up and the spin on site 2 is down, and vice versa. You would call a spin singlet state. So that hence the word valence bond. This is a covalent bond in organic chemistry. So there's a covalent bond between the 2 electrons in that case, which is with spins being up, down, minus, down, up. So it's a spin singlet state, which would then, and these spin singlets have, or these valence bonds have formed a lattice, a regular lattice, and hence it's called a VBS or a valence bond solid. So this state also breaks symmetries. It breaks the translational symmetry, but in a different way from the checkerboard state. It also breaks a lattice rotation symmetry. And so the degeneracy of this state is 4. There are 4 such states you can make, depending on the 4 directions the valence bond could point. All right, so these are all conventional states. They have some, more complicated spatial structure, but in the end, they're not the true exotic states that we are trying to move towards. Okay, any questions so far?
Sorry, are these 1, 2 labels correct on the spin arrows?
So the one, this is meant to be a label representing the site. So I have 2 sites, 1 and 2. So this says site 1 has spin up and site 2 has spin down. And oh, yes, you're right. Okay. So this should be, let's see, I don't know, with this thing I am using PowerPoint. I can't quite erase. Okay, thank you.
Yeah, okay, because it looked a little bit like 0.
It's 1, 2.
Yeah, thank you.
Okay, there we go. That's correct. Thank you.
Thank you.
All right, so that's the valence bond solid, and nothing too exciting. You can understand it by the mean field methods we've developed so far, just a bit more complexity because of the spatial structure. All right, so let's go to the exciting stuff. So the idea of this actually in some ways goes back to Pauling in the early days of quantum chemistry. Well, even further back, there's Kekulé, who came up with the resonating valence bond picture for benzene, where you have 2 possible resonance valence bond configurations around a hexagon, and they resonate to give you benzene. And then Pauling suggested that this was a theory of metal like lithium. He wrote down what's now called the RBB wave function as a description of lithium. Now, Pauling was wrong in a sense, this was before Bloch's theorem. Pauling didn't know about Bloch's theorem or didn't believe it. Now we know, of course, the way to understand a metal like lithium is to use Bloch's theorem and find the plane wave states and ignore the interactions to begin with, and just put it in and occupy the states inside the Fermi sphere. That was chapter 1. However, in 1974, a long time ago, Anderson and Fazekas, found the right setting for Pauling's resonating volume wave function, which is the model we're talking about now. Spin models of various types with strong interactions, which are insulators if you think of the spins being electrons or charge carriers. So the picture is very simple. It's like a valence bond solid, where the spins start to form singlets with each other. So each ellipse here is up, down, minus down, up. But the ground state is a superposition. It's an entangled state, we'd say today, between different configurations, different valence bond pairing. So there's an exponentially large number of such pairing, exponentially large in the size of the lattice, and the ground state is the sum. Here's a variational estimate. We don't know. It's obviously for a given model that won't be very good necessarily, but we're just trying to understand a few things about such states. So it's each D here represents some dimer covering. So each D, this is one possible D, but there's an infinite number, well, very, very large number of them. So the number of dimer coverings of the triangular lattice in this case, with some coefficient CD. And what these coefficients are, who knows, very hard to compute, but they are basically non-zero or of roughly the same magnitude for all of the dimer coverings. I'm going to, yes.
Should we think of like an experimental realization of this as like at the half filling type area on like a triangular lattice in the Bose-Hubbard model, or is this still?
Right. It could be bosons, hardcore bosons at half filling in the triangular lattice, for example. Yeah, but there are many other possibilities. Now, the XXZ model on a triangular lattice has been studied, and in the end probably doesn't do what this picture shows, but there are, could be other models that are not too far away.
Okay.
And these days there are these Rydberg atom models that Misha is studying. Misha's group is studying, and they could well be realizing some of these phases. There's going to be a bunch of papers on that coming out soon. Okay. All right, but without getting too specific, we just want to understand a bit about the structure of those phases. So also I should say that you could imagine more complicated states where you have singlets between next nearest neighbors and third neighbors and so on. And those, you could imagine you had a few terms like that too. They're not all orthogonal to each other, so it's not clear whether you're really adding new states. But you could also imagine states where these dimers are quite long range, and those, anyway, understanding and classifying those states is now much better understood. In the last, I would say in the last 10-15 years, we have a full theory of it. But let me for now just use just give you an intuitive picture using these simple pictures. So the picture I'm going to present now is basically correct for certain states, with the assumption that all these CDs can be chosen to be real. So that's something I'm going to assume in this discussion. They need not be for other models, but let's just, for now, we just assume there's some real number. Okay, so the ground state. So continuing the same vein of just trying to think about excitations, you could imagine an excitation like this, where this spin decides not to be paired. So it's going to move around, and that unpaired spin is called a spin-on for obvious reasons in the antiferromagnetic language. It turns out that there are two types of spin-ons, and they're called E or epsilon, and we'll come to that. And whether they are boson or fermion is also another subtle things, but we're going to come to many of those things. But for now, okay, there's some excitation like this, which is a spin on. And let's try to think about it in the boson language. So suppose this was my ground state, and I hit the state B dagger on this state. Then what I'm going to get, so I'm just adding one boson. I'm adding one boson to the ground state, the big boson. And that will convert it to both spins up, because now there's two bosons. There was one boson to begin with between those two states. I added one more, and so now there's two bosons. And now these two can move apart. And so what we see immediately, the fact that, this seemed like a nice wave function right now. This is quite a remarkable wave function, because what's the boson number carried by this relative to, to the ground state? I added one boson to the ground state, and I've got these two excitations which are moving far apart, and really one could be on the moon and this is over here. So I only see one of them. And that one, what's its boson number? Well, its boson number is a half. Also, spin is a half, but it's more dramatic when you think in terms of boson number. So there's your remarkable feature of the state. If this whole picture is correct, that you have excitations with half a boson number, because you created two of them by just adding one boson. Okay, so this also tells you that you couldn't possibly create this spin-on or this excitation on its own. There's nothing you could do in any experiment, or even by perturbing the system in any way you wanted, to create just one of them. You always create them in pairs, but once you create them in pairs, you can separate them. And that, in some sense, that property, that there's no local operator that can ever take you from the ground state to the one spin-on state, is nowadays the key to what's called topological protection. That there are these sectors of the Hilbert space. There's a sector where there's no spin-on, and there's a sector with one spin-on, and there's no matrix element that can take you between them. So if you formed a qubit with those two sectors, that qubit would be protected. So there's some kind of quantum. So that's the idea of Kitaev, of how you could use the state to do protected quantum computation. Okay. All right. So that's the one. Oops. Let me go back. Okay. So that's one exotic excitation. Actually, there's two of them, but we'll come to that in a minute. But there's another. It turns out, and this is part of the things that were learned much later, not realized by Anderson in the early days, that there's any such state in which the picture represented to you makes sense, is stable in some sense, must have some other excitations. This is not the only property it has, an excitation with boson number 1/2. The whole theory is not consistent unless there's another type of excitation around. And what is that excitation? Well, it has various names. I guess it was discovered first in condensed matter and called a vison, not by the original people who discovered it. But now, because of the connection to toric core, which I think how you will discuss in tomorrow's section, sometimes called an M particle. Anyway, but here's what it is in this valence bound language. So I told you the ground state was sum on D CD times D. So I'm going to create another excitation, which, as we'll see, hopefully maybe even by the end of this week, is like a close analog to the Abrikosov vortex of a superconductor. It's like a vortex, and hence the word vison, V, is supposed to represent vortex, and the I is because, well, it's not really a vortex of a U1 gauge theory, which is what the case for the Abrikosov vortex, but it's really a vortex in the Ising gauge theory. Hence the word. That's how the Fisher and Senthil came up with the word vison. All right, so I'll use the word vison, or M. We'll see. So this is a trial wave function for a vison. You take the same ground state roughly, but you deform it in this manner. You put a phase factor of -1 or +1, depending on D. And how do you choose it? Well, you first of all, you pick a center of it. And now you're going to deform the wave function globally, really all over space. But you're going to do it in a way that the region far away doesn't cost you any energy. All the cost in energy will be around here. So you just pick a line starting from the point, any line. It doesn't matter which line in the end. It just goes off to infinity. Or really, it'll end at another vison somewhere else. But it can't just stop. So it's a highly non-local change. And that's, of course, again, behind the topological protection. And what you do is you pick this line. And once you fix the line, you count the number of dimers crossing it. So in this case, there's just one dimer. So I'm assuming this is infinity. So therefore, for this dimer configuration, I'm going to get a -1. So ND is basically the number of dimers crossing the red line. Okay, so this gets a -1. This still gets a -1, and so on. That gets a -1, and so on. That gets a +1, and this gets a +1, and so on. Okay. So that's the trial wave function. So one thing you have to convince yourself is that this thing will, that this cut is totally unphysical. It's not going to cost you any energy. It's invisible. It's very much like, in a vortex. You say the phase of a vortex goes from theta, goes from 0 to 2 pi. So if you write down the value of theta, there's kind of like a branch cut going from where the phase jump from 0 to 2 pi. But, that's totally fake, because the only thing that matters is e to the I theta. And so you can put the branch cut anywhere you want. The only thing. So here it's a little more subtle. It turns out it doesn't matter where you put the cut. It's basically the same wave function. And the reason is, if you try to compute any property, expectation value, any operators, which involves taking two of the wave functions, those operators end up involving taking products over dimers that on closed loops. So if you take any closed loop, then so if you take a closed loop, well, any closed loop out here will cross the dashed red line twice, and so it ends up costing no energy, because for those closed loops, you always have an even number of dimers crossing the line. So the only place you actually get some difference and some cost you energy is a closed loop that encircles the center of the vortex. So all the energy cost will be in here. Okay, we're going to do a calculation where we're actually going to see all that worked out. All right. So with that assertion, this is just to give you a rough idea. So that's a new type of excitation any such what's called a Z2 spin liquid should have. Okay. So now I've identified two types of excitations, which is the spin-on and the vison. And now these are turned out to be anyons. And the reason is the following. Suppose I had a spin-on. I had this. If you go back and look at the spin-on, so when the spin-on moves, you see it moves the valence bond. This valence bond, it can only move by moving a valence bond out of its way. And so it ends up, it's hopping, picks up a phase factor, which is associated with the phase factor associated with that valence bond. So now imagine taking a spin-on. So you have a vison sitting here. And you take a spin-on and move it on a big loop around the vison. Well, as the spin-on goes around, it will cross the vison to this branch cut once. So no matter where you put it, it'll cross it only once. So because it's encircling, the pickup of phase factor, the spin-on wave function as it goes around will have changed by -1. So that's called a statistical phase factor. And so therefore, and in fact, it's -1. And it's between two different particles, a spin-on and a vison. So these are what are called mutual semions, for obscure reasons that will become clear when we talk about Chern-Simons gauge theories later on. In fact, this whole thing can be described by a rather complicated Chern-Simons gauge theory. And we probably will talk about it eventually. Okay, so that tells us that there's something anyonic about this. Spin-ons and visons are mutual semi-ons because taking any one around the other makes them, you get this phase factor of -1. Okay, yes.
Should the visons also be created in pairs?
Yes, no, thank you, right. So the visons are also can only be created in pairs because this branch cut has to end somewhere. Any local operator can't make an infinite change out to infinity. It can only create a branch cut over a given region. And so wherever the branch cut ends would be another vison, right? So they share that property with the spin-on. Okay, so then I've said the visons and the spin-ons are mutual semi-ons. And now this is another remarkable thing. I guess was pointed out by Reed and Chakrabarty. That if you take a bound state, suppose you know, there was a lot of argument in the early days of, you know, is this spin-on a boson or a fermion? It all depends into what kind of phase factors, plus and minus ones, you put on the CD. That's our understanding today, which I haven't specified anyway. So, but suppose you had a spin-on, and I should really draw a picture here. So, and then I put a vison near it. Okay, oh, no, sorry. I have a vison here, and I put a spin-on near it. So maybe this side was a spin-on, and then the bonds rearrange in some nice way. Okay, so now I have a spin-on sitting there, and now I have this composite object sitting here. And let's imagine that the spin-ons are bosons. So if I take a spin-on around each other, exchange it that way, it's just a boson, you don't get any phase factor. But now imagine I have a spin-on vison bound state, like this, shown here, and I have two of these bound states, and I move one around the other. Okay, you have to draw a picture now, and in this keynote, what should I think I have to, let's see if I can do this. Okay, so now I have to create another slide. No. Oh, over here. Okay. Okay, so here I have a spin-on sitting here. I have a spin-on sitting here. And then I also make a vison. And this, let's say for convenience, has a branch cut going this way. And this has a branch cut going this way. And then I'm going to do a process in which I'm going to move it around, move this guy from here to there. Okay, so that's going to be some parallel transfer. Slowly move this around and ask what happens. But what's going to happen as you move this over there, that this branch cut is going to cross this spin-on. So you pick up a -1. Then this spin-on here crosses this branch cut as you move it over. And you can try to see it. And then in the end, you want to end up with the same configuration. So you move this over, and then you translate them both back to get back to this initial state, and you know, effectively exchange the particles. And you can then work out, no matter how you do it, as long as you end up with the same state, you'll pick up a phase factor of -1. So that's a remarkable result, that a bound state, if the original spin-on was a boson, and you bind it with a vison, the bound state then is a fermion. And vice versa, if the original spin-on was a fermion, you bound it with a vison, then that bound state is a boson. So there was a, you know, in the early days of when these spin liquids were discussed in the, I'd say the early 90s, maybe the late 90s, there was a lot of argument. You know, my theory is better than yours because I have a bosonic spin-on, and your theory is a fermionic spin-on, and bosonic spins are better, or whatever. What we now know is that that was a, you know, in effect, everybody was right. It's just a question of which both of those have to be present in the system. Otherwise, the whole thing isn't consistent. So the bosonic spin-on I call E, and the fermionic spin-on is sometimes called an epsilon. So this state that when you bind a vison with an E, M with an E, you get an epsilon. bind a vison with a bosonic spin-on, you get a fermionic spin-on. This is now called a fusion rule in the theory of topological states. So this is the fusion rule, very simple. E cross M is epsilon, and vice versa. Epsilon cross M is an E. And you can also write down the fusion rule because you can, what if you bring two spin-ons to next to each other? Well, E cross E, is written as one because you can, a local operator can act on the ground state and create two E's. So E cross E is equivalent to the ground state sector plus local operators. And so all of these fusion rules are to be understood in that regard. So if you had an E particle well separated from all other particles, and you had an M particle well separated from all other particles, so there were different sectors of the theory, you brought them together, you fuse them, then that combined sector will be the same as an epsilon sector, up to local operators. Okay.
Sorry, Subir, can I ask a question?
Yes. Sure.
So I'm a little bit confused. So when you showed these two, things being exchanged with each other, these two bounce, you kind of chose the two branch cuts to kind of, I guess, be pointing in the same direction, and that's kind of why one had to intersect the other. But why couldn't I make, a different choice where the two branch cuts are going off in different directions?
Yeah, well, I think you have to make sure that after the exchange, everything looks the same. You have to exchange them and translate them and make sure that the state that you get up at the end looks exactly the same that you started with, other than the fact that you've exchanged the two particles. So the branch cuts also have to match in the initial and final configurations. And I think that if you try to do that, you'll find that it all works out.
Okay, gotcha. And then maybe another slightly more naive question. Yeah. You told us how to make a spin-on just by, adding a boson to the state.
Yeah.
Is it clear how to make a vison?
No, not at all. Yeah, it's just, it's the same question. How do you make a vortex? Well, you have to know something about in a superconductor. Well, we now know that a vortex coupled to magnetic field. So in that case, when you apply the magnetic field, you could make the energy of a vortex be preferred, and you get the some kind of vortex lattice in type 2 superconductors. Yeah, so here this is that's one of the things about all these topological excitations. They're very well protected, but that also, the flip side of that, they're almost very, very difficult to create because any local operator doesn't. So you have to then be more creative. Yeah, you just have to hope something creates them, a pair of them, and you're able to separate them somehow, I suppose. Yeah.
Okay, thank you.
So yes.
Excuse me. I noticed you didn't do YouTube live today. Just let you know.
I know. That was the technical difficulty. I was trying to run YouTube and it wouldn't run. It just kept crashing. I don't know what happened.
Okay, no problem. The email login problem.
Yeah, I mean, I'll of course going to post the Zoom recording, but unfortunately, this lecture there's no YouTube. I can try one more time, but it's already, most of it's over. Yeah, I don't know what happened. Maybe they changed the permissions and something.
No worries, thank
on Zoom. Yeah, there was some problem with Zoom said I don't have permission to do this. It may have been because I didn't start it properly and I wasn't a host. Yeah. Sorry about that. Okay. So another property that follows from just these simple wave functions and this general arguments is degeneracy on a torus. So imagine I took the picture that I just showed you and placed it on a torus. So I had the resonating valence bond. The wave function is now periodic in both directions. So this is the ground state, and I have some wave function. But now consider the following state, where I take this branch cut that I've been talking about for a vison and make a branch cut around here. So any dimer that crossed this branch cut picks up a -1. We already told you the branch cut doesn't cost any energy except where it ends. Well, in this case, it doesn't end anywhere. So basically, this branch cut costs 0 energy. Well, it costs a little bit of energy, which will be exponential in the system size. So divided by some correlation length. Okay. So so therefore you would say, well, there's a degenerate ground state, which is has almost the same energy, and this doesn't depend really on any broken symmetry or anything. It's just a state I can form by having that long-range entangled state. Another way to think about it, in terms of, rather than thinking about phase factors, is the following. So suppose I have some dimer configuration here. This is sitting on a torus, and I make and I just pick a branch cut like this. And let me just count the number of dimers crossing this line. So in this case, it's 4, and I rearrange the dimers in some way in my wave function. And what you'll find is that, okay, it's 4, 4, now it's 2, that the number of dimers crossing the line is always, by any local move, is preserved modulo 2. So if you think of the Hamiltonian as only forming local moves, it seems as if there's 2 different sectors to the Hilbert space, which cannot be connected by any finite number of operations of the local Hamiltonian. And one sector is with even number of dimers and the others with odd number of dimers. So there's twofold degeneracy for that cut. So the vison way of thinking about it was the linear, odd and even combinations of these numbers across the cut. All right, so there's a twofold degeneracy, and in fact, okay, you can also put the cut in the other direction. You can put a cut in this direction, so you'll get another ground state, or you can put it, oh sorry, not there. You can put a cut in this direction, like that, not that. Okay, so that will give you another ground state, and you can put them in both and to get the 4th state. So there's a 4-fold degeneracy of this state on a torus. And then you can find, suppose I put it on a more complicated object with higher genus, the degeneracy will depend on the genus. And that's the origin of the world of topological degeneracy, because it depends on the topology of space and how, what the genus of, how many handles it has and so on. Okay. All right, so let me just summarize what I've just kind of told you out of thin air. And the remarkable thing is, well, okay, there were a lot of calculations along the way, but much of this was, well, everything I've said so far was very well understood. And then there was Kiteo's beautiful paper, which found an exactly solvable model with all of these properties. And okay, before that, people were skeptical that something like this even existed. All right, so today we characterize this phase state by a bunch of properties, and I'll just summarize the properties. And we're going to actually do calculation where we'll see most of these properties appear. So the statement is that the people, and today it's all part of branch of mathematics called unitary modular tensor category theory or something like that. And this is how mathematicians will talk about it. There are 4, sometimes called super selection sectors, or 4 types of anyons. There's the ground state sector, which is just called 1, or the trivial sector. Then the E sector, the M sector, and the epsilon sector. And you can't go between any sectors by any local operator. So then, yeah, okay, this is just the word, and then the spin-ons. Now, in some cases, they can be a global U1 symmetry. Like if you had a boson system and the boson number is conserved, then you can ask, what are the quantum numbers carried by these sectors? And it's conventional to put, if there was a boson number, that the E and the epsilon are the ones that carry the boson number, not the M. In fact, everything we talk about in terms of topology is invariant on the interchange of M and E. If there's a kind of duality transform between the two of them. But once you have a global conservation law, like the boson number, then yeah, it's conventional to separate them by calling the one with the boson number, half boson number, the E part. All right, so again, as I said, The M itself is a boson. That's kind of easy to see. You don't M doesn't pick up any phase factor when you move them around each other. But E and M are bosons, and conventionally E is called a boson and epsilon is a fermion. Okay. And now by the kind of pictures I drew, you can figure out that it doesn't matter. You pick any two of them, you'll get a phase factor of -1. And these are the fusion rules. I've already told you, I think I've mentioned all of them. You know, this fusion rule, for example, M cross M is 1, is simply the statement that a local operation on any local operation on the ground state, what I call the ground state, is equivalent to, can only create a pair of M's or a pair of epsilon or a pair of E's. Okay. All of these, so this is the simplest set of, you know, such rules for a topological state. There are, of course, many more complicated ones. The other simple one is the Laughlin fractional quantum Hall state, which we will also talk about. But that breaks time reversal symmetry. This one, time reversal is not an issue. Okay, so it has a fourfold ground state degeneracy on the torus. I've talked about that. All right, this is what we get to in the next lecture, I think. If not, yeah, it has an emergent deconfined Z2 gauge field. It's really a Z2 gauge theory, and we'll see what I mean by that. Okay, this is also something we'll see when we talk about fractional quantum Hall effect. Certain topological states have protected low energy excitations on their edge. This one doesn't, but sometimes it can, if you have special symmetries. Oops. And there's also topological entanglement entropy, which I haven't talked about. That could be a topic for somebody's presentation if you care to talk about that. I don't think I'll cover that in the course. Okay. Oh, finally, to complete the story, yeah, I'm getting probably, this is the most advanced part, which is only slowly been understood recently, completely, I would say. It turns out that there's further additional properties of the Z2 spin liquid when it appears for bosons at integer or half integer filling, which is the model we motivated it by. So the toric code model doesn't have any of these properties. And these properties have to do with something called an anomaly. And in this case, the anomaly has to do with what happens when you take a vison and move it around any site. And so we'll actually show you, I'll actually compute that for you. And what you find is that for half integer spin or half filling of any half integer filling of bosons, the visons pick up a phase factor of -1. So here, what I'm doing here is you have a site here. So here's your sites of the square lattice where the bosons sit. And the vison, the M particle is sitting here. And so I'm saying, what's the difference between Tx, Ty, or Ty, Tx, which means, oh, what did I do? Oh, gosh. Okay, I have to draw that again. Here's my lattice. And I have a vison. And then I apply on it first Ty, and well, okay, first Tx and Ty. Or I go this way, Ty, Tx, and I end up there. The question is, do I end up with the same, just the original vison state that's been translated, or something else? Are the two states by that way of doing it the same? And it turns out they're not. And that depends on the filling fraction, whether it's half or 1, and has to do with the fact that on the average, there's a boson there, half a boson there. So there are these quite remarkable properties that are also very fundamental properties of this state, but associated with the fact that there's a global symmetry and their translations. So this, for Juven's benefit, if not anybody else, this is some kind of tooth anomaly in the global U1 plus the translation that's present in this theory. Okay. All right. So that was meant to be just an impressionistic survey of where we're going to go in the next week. I think we'll cover many of these things by an actual calculation. And this will give you, flavor of, just a remarkable new type of phase of matter that we're going to talk a lot more about in many different contexts, where you have fractionalization and you have these, at least in 2 dimensions, you also have anyonic particles of different types. And all of this, was just something of interest to some crazy physicists, but when Kitaev pointed out this could be used for topologically protected quantum computing, the rest of the world certainly got very interested. Okay. Questions? Maybe I should put this. Yeah, this is the part that's more comprehensible to you at this stage. So all of these properties are properties of the toric code or boson systems or anything. Well, except of course this one line here. But the anomaly has to do with very special types of systems with special symmetries. So the topological properties have nothing to do with any symmetry. They're just properties a system could have if you got lucky. And once it has it, they're very robust. Questions?
I had a question about the epsilon, the bound state of the E and M particle.
Yeah.
Like, what does it look like?
Yeah.
The wave function. We saw E and M, but like, what does the epsilon look like?
Well, the best I can do is what I just showed you. I think those things have been deleted in this. Well, I can draw it again. Okay. Yeah. So, I mean, literally, you have to take. Well, if I did the square lattice, I have a vison here, and then I have a free particle here, and then I have singlet bonds elsewhere. Some of them can cross this line. Okay. So you have all these singlet bonds, and they're all resonating around, and then you have the M particle here, and they say the E particle here, and the E particle is also moving around, but it's not going too far. It can move from here to there, where the singlet bonds moves. So it's just a cloud of all of these. Where the constant factor is in this cloud, there's a branch cut, and there's a spin a half moving around in that region. Further details will depend upon, the specific model you're looking at, and quite hard to compute, but that is the mental picture, that there's a region here. You've got both the absence of a dimer with a free spin, and you've got a branch cut. And they're moving around in the superposition of all this mess. So certainly all the phase factors and the C sub D will change, but they're only going to change in this region, not too far from where the spin-on and the vison are.
And why does it not like move away too far?
Well,
like,
it could, yeah. It could, yeah. It could work. It could be that the epsilon particle is unstable to E or to E and M. It could basically not exist as a bound state. That's possible. So that's that's a good question. So when people talk about topology, when mathematicians discuss this, sometimes I get a little lost because there's no Hamiltonian or anything in their discussion. So what a mathematician would say that somehow you tuned your Hamiltonian by you put in some trapping potential, who knows what. If you could get these two things in the nearby, you put all kinds of local operations and you got this thing nearby, then it'll have the topological properties of an epsilon particle. A separate question is this bound state stable? For example, for epsilon decaying to E and M moving off to infinity as well-defined quasi-particles. So does this epsilon actually exist as a quasi-particle that you could see in an experiment? That's a dynamical question, depends on the Hamiltonian. It may not. The statement really is that if by a sufficiently clever experiment, you formed an excited state where you had this epsilon sitting here for a while, it will always be there. The only way you could destroy it by bringing another epsilon nearby or these two E and M's moving off to infinity. But no local. So if you did an experiment, a time-dependent experiment, and you formed an epsilon particle near, you're pretty confident that it's just going to stay there for a while. It can't just disappear into nothing. You know, it's always has that topological property. Yeah, but you're right. I should have emphasized that the Brown state may not even be stable. Yeah, that's a separate question. That's a physics question, not a topological question.
I see. I think I also have a related question. Like here, unlike what we've been doing so far, like we usually talk about a Hamiltonian and then talk about the ground state. Here somehow like we're doing it the other way around. I was wondering like what that.
Yeah, well, wait till next lecture. So I just thought it'd be a good idea to give you the very topological picture just by drawing a few pictures. Next lecture, we are going to start with the Hamiltonian and do some calculations. But the calculations are approximate, so you know that has its limitations too, because we are dealing with a strongly interacting system, and short of some very sophisticated numerical work on a computer, that calculation is not going to prove that such a state exists for a certain Hamiltonian. But it can at least show you the way on what are the possible types of states.
Yeah. Thanks.
So I have a somewhat, I don't know, impressionistic question perhaps, but like, what is the spectrum of this? If you imagine you have a valence bond solid, you have very highly degenerate ground state manifold, right?
Sorry, which valence bond solid? You mean
like on a triangular lattice, let's say.
Well, you mean it's called a valence bond liquid or?
Oh, sure.
A resonating valence bond. Yeah. Okay. This
so, and if you create this like topological, you pay some like a vortex.
No, this is one state. This is not nothing highly degenerate. There's only one state, G. There's only one state. It has many configurations. It's a superposition of all of these. It's just one state. There's nothing degenerate about it. It's just one state.
Okay.
I mean, I'm showing you many pictures. The pictures are different components of the wave function of one state.
So this is the optimal dimer configuration, I guess, is what you're saying.
No. So this picture is one of the Ds.
No, G is the
actual state.
Ground state.
Yeah, but this picture is just one of the Ds.
Right.
Then this picture is another one of the Ds. And the ground state is the sum of all of them with some coefficients.
Okay, but then if this is the ground state, you're creating excitations on top of this ground state that pay this vortex?
Right, okay. Now, so this is all the ground state. Now this is an excitation. Yeah, so this will cost some energy, it will have some dispersion. And in fact, next lecture, we will compute in a certain model what that energy is, and or at least show how to compute it and actually even compute the dispersion. Yeah.
And this is a gap dispersion because of this?
Yes, so for the type of topological states I'm talking about, everything has to have a gap. Yes.
Okay. Thanks.
So there is another type of zeta spin liquid which can have gapless excitations, but yeah, I mean, in fact, the Kitaev honeycomb model does it. Yeah, I think it has a regime which is gapless. Yeah.
Thanks.
But I'm talking about, I will talk about the gap case.
So does this depend at all on the lattice geometry?
Absolutely. I mean, I showed you all these other boring states to begin the discussion. Well, they're not boring. I like a lot of these states too. So whether you get the checkerboard pattern, or you get the X ferromagnet, or the valence bond solid, or the valence bond Z to spin liquid, certainly depends which is more likely, I think, these kind of things, in fact, are more likely in the Kagome lattice and less likely on the square lattice. It depends on how long range the interactions are. It depends on really everything. But there is, that's one of the very difficult problems, to figure out where you find such a state.
But you did mention that there's, a resonating valence bond state on a square lattice as well, right?
In principle, it can exist, but for the nearest neighbor square lattice antiferromagnet, we know it doesn't exist.
I see. So that has to do with kind of the Hamiltonian?
Yes, yes.
Okay.
But in principle, there can be a Z2 spin liquid on the square lattice too. Yes.
Okay. And is this state somehow? Sorry.
It has to be a more complicated Hamiltonian than the ones I've written down. Yeah. Go ahead.
Okay. And then is this state somehow like equivalent to the toric code? This dimer covering?
So no, it's not equivalent. I mean, so there are a certain set of basic topological properties. I guess these are properties that are all summarized on this slide. So all these properties here, all of these properties, well, except this one. So let me just delete this one, because there's no concept of a boson number in the toric code. All of these properties are satisfied both by the toric code, or anything that anybody would call a Z2 spin liquid would have all of these properties, every one of these properties. And one of the things a mathematical view of these theories has shown us is that they're really rigidly tied to each other. You couldn't have, for example, the spin on and not have the M, and the whole thing would be inconsistent. So these are all, and have this, fourfold degeneracy. They're all rigidly tied to each other. And there's some classification of what are the other types of topological states. And that's, well beyond my pay grade. There's a lot of very sophisticated mathematics in doing that kind of thing. So, however, when you add certain symmetries, like you have a boson number, then there can be additional properties, which are typically associated with anomalies, associated with the symmetries. Like, is there any difference between a Z2 spin liquid for bosons at integer filling as opposed to bosons at half integer filling? Now, this for physical application, this turns out to be a really crucial issue. Although people quantum computing don't care about this, but this turned out to be really crucial for understanding real models, these anomalies. And then this, so the anomaly is not something you can make any sense of in the toric code. These are not property of the toric codes.
Okay, gotcha. Thank you.
Sure.
Maybe no one asked. I have one.
Sure.
Subir, can you explain again? This is not a typical model I study, so this is a naive question. How do you identify the vison again? And also, how do you identify the branch cut? It should be related to some kind of Z2 magnetic flux, right? That part I didn't see clearly from, maybe you draw, but I didn't see from the latest model. How do you identify the branch cut?
So I just ask you to wait till next lecture. We are moving towards that direction. We are going to actually do a calculation where we're going to see all of these things come out from.
But I think the question is about the picture. That how do you see this excitation out of the singlet, the C of the singlet state? Where do you draw the vison, and where do you see the?
Well, the vison, in general, it's a quasi-particle like any other quasi-particle. So it will have some mass and some dispersion and some energy gap. So I am just trying to write down some trial wave function for it. Okay. So what I imagine is that it's really a plane wave. The actual vison is a plane wave. But I imagine that I'm looking at a component of the plane wave where the vison center is sitting here, sitting at this point. Okay. In the toric code, in fact, the vison has infinite mass. So you can put it anywhere. without any energy cost. In a real system, it'll have a mass and will be in the plane wave state. So it's really a plane wave. This thing, the actual wave function I'm talking about, the actual wave function, the vison wave function has some momentum k, and it's sum on k e to the I k dot r with some state r. So what I've shown you is a picture of the state r. Oh, I don't know why that erased. This is a picture of that, the state sitting at the point at the origin r, and I have to take a superposition of all these states to form the actual vison state. So the state r is everything I've shown you here, plus all the dimer configuration. And now you're asking about the branch cut. Well, the branch cut, as we'll see, is just a gauge choice. You can choose another gauge, and it'll be somewhere else. It doesn't matter. And we're going to see that very explicitly when we do the calculation. Just wait next week, Wednesday.
Do you need to add some Hamiltonian term to like RVB resonant valence bond Hamiltonian? You have to add additional term.
There is no RVB Hamiltonian that I know of. I mean, there's an RVB wave function. So this is another wave function. So I think it was Reed and Chakraborty who realized that once you had the RVB wave function, you could form a wave function of these visons of this state. And this would be orthogonal to the ground state. Then they argued why it had to be orthogonal. And so this is an excitation that has to exist. Well, I haven't proved. I think it'll become much clearer once you see an actual calculation, which I'll show you next on Wednesday.
Thanks. Thank you.
Can I ask a quick question, Sabir?
Yes.
So are these, you mentioned that you have some emergent Z2 valued gauge fields that comes out of
Yes.
this type of model. Is that a general feature for these topological phases of matter? You get some emergent gauge field out of them at low energy, or?
Yes, absolutely. Yes. It's these gauge fields that, that's often in the end, the description that you end up with. And the gauge fields, they give you, the most important effect are Aronoff-Bohm phases. They can give you Aronoff-Bohm phases when things move around each other. When you have a flux of a gauge field and you move around it, you pick up an Aronoff-Bohm phase factor. And you can think of invariably these Anyonic phase factors as coming from the Aronoff-Bohm phase factors from the gauge field. So as a physicist, if you want to write down actual theories which has some dynamics, you invariably have to have the gauge field if you want to talk about more than energies, more than just statistics. If you want to really talk about energies and time dependence of things, then you will end up having to use a gauge theory. But if you're a mathematician who only cares about topological properties, where everything has energy 0 or infinity, well, then you can ignore the gauge field and just talk about the E, the M's, and the epsilon, and various algebraic properties that they satisfy.
Sounds really cool. Do you know if there's, so I know for like gauge theories that are coming from like compact Lie groups, there's a whole theory about the topology of such gauge theories that comes from like, Chern-Simons theory and these characteristic classes. Is there such a theory for these gauge groups that are not continuous and discrete?
Absolutely, yeah. So, in fact, I'm not an expert on this, but I think at least certainly all the topological phases that I know and understand, it may not be true for every one of them, but as far as I know, it's true, can be described in terms of an appropriate gauge theory with the appropriate number of Higgs fields with an appropriate Chern-Simons term. There's always such a construction for essentially all of these topological phases. Maybe Juven can correct me if there's any cases where you can't do that.
Okay, so in any dimension, actually also including 2 + 1, 3 + 1, any dimensions, you can use the finite group. And finite group, starting a gauge group with finite group and write down a gauge theory for that. That will be a TQ of T, topological field theory at low energy.
Yes. Right.
And that's a question that he wanted, that you don't require a compact Lie group, but instead a discrete gauge group.
Sure.
And Dargo-Witten person, or the people who formulated in 1990, these are finite gauge, finite group. But Chen-Simon theory.
No. The Dirac-Witten were talking about SPT phases, I thought. That's
No.
No? Okay.
Dargo-Witten actually is originally a gauge theory with dynamical gauge field.
I know.
The relation to Chen-Simon SPT, the relation to SPT is after you gauge the global symmetry of SPT for finite group symmetry, you will get Dargo-Witten. That's one step. One is the one is
okay.
SPT, no entanglement, short range. The other is Dargo-Witten, actually is long, but that's not language they use. So, but they just formulate gauge theory, finite group gauge theory.
Okay.
But in a lower dimension, plus 1D will related to a Chen-Simon theory, what Subir just mentioned. But in that case, the gauge group for Chen-Simon does not require to be finite group only, but it can also be a continuous Lie group, like SU2, SO3, with certain level quantized. Yeah, that's special for
okay.
Right. Okay.
All right. So we're going to learn a lot of this. Not everything Ewan said, but some reasonable fraction of it as we go along. But one general remark I would say, yeah, once you allow yourself to have all kinds of particles with all kinds of gauge charges, the possibilities are very rich. But from my point of view, I mean, I think the hard question really, and really the important question for the physics is how do you get these phases in a model that didn't have a gauge theory? I'm just starting with the Hubbard model or something like that, or XXC model that has no gauge fields whatsoever. But really, what we want to learn is how is it that how fractionalization occurs on its own when you're not a particle physicist and free to invent all kinds of particles, all kinds of gauge charges. We're just dealing with some well-defined particles with short-range interactions, and amazingly, they end up in phases where they have fractionalized particles which carry gauges, and how that emergence occurs is what we are after. Okay. Okay, I think we'll stop there. And
yeah, I think there is still one question in the chat. Maybe you want to answer that.
Okay, now I have to figure out how to read the chat. Let me stop sharing, then I can see the chat. Yes. When you say excitation with spin on its side as I and J, do you mean the state? Spin on side I, spin on side J? Absolutely, yes. So the question is, if I have two spin-ons at sites I and J, do I mean spin-ons, free spins on those two sides, plus the sum of many, many diamond configurations? Yes. But what I can say further, if the spin-ons are far enough apart, and I'm looking at a region where there's no spin-ons, some region over here, then all the phase factors in the CDs will be the same as in the ground state. They only change near each spin-on. Okay. All right then. Okay, so see you tomorrow morning, or if not on Wednesday. Okay, thanks. And sorry for the technical difficulties. No YouTube for this talk.